This is John Whitaker for the Mathematical Analysis 2 class. And this is our 7th video lecture. And last time we ended up talking about derivatives of complex value functions. And I want to start off today by giving 2 facts about derivatives of complex value functions. The first of which is the following theorem. We're going to say, we're going to let f be a complex function defined on A to B if f is differentiable at some x in A to B, then f is continuous at x. So this is a fact that is analogous to the fact about a real value function. The differentiability implies continuity. A similar fact about differentiation rules for complex value functions is the following. We're going to let f and g be complex functions defined on A to B, and we're going to say about f and g that they are differentiable at a point x this element of A to B, then f plus g, f times g, and f divided by g are differentiable at x. And not only that, but we have formulas. First is f plus g prime evaluated at x is equal to f prime of x, f of x times g prime of x plus g of x. I'm sorry, I'm not paying attention. F plus g prime of x is f prime of x plus g prime of x. B, 2, f times g prime acting on x. The product rule still exists here. It's f of x times g prime of x plus it's f prime of x times g of x. And thirdly, f divided by g's derivative, evaluated x, is equal to g of x times f prime of x minus f of x times g prime of x all over g of x to b squared, where g of x is different from 0. That's the quotient rule. And I am not going to prove that theorem either, but just state it. Next, we're going to talk about derivatives of functions that are vector value functions in terms of Euclidean space output values. And the way that we're going to think about them is given through this fact, is we're going to let f bar be a vector value function on A to B. That is, what we're thinking is that f goes from A to B into Rk, where, if you recall, Rk is equal to the set of all x sub 1, comma x sub 2, all the way up to x sub k, so k tuples, okay, with x sub I being an element of R. And that's for all I with 1 less than or equal to I less than or equal to k. Then f bar of t is really defined by, or given by f sub 1 acting on t, comma f sub 2 acting on t, all the way up to f sub k acting on t. And so that's the way we can think of f bar. And we'll say something about these coordinate functions. Namely, where fi is a real function on A to B. Okay, so in viewing vector value functions in this light, we have a definition here. We say let f bar be a function that goes from A to B into Rk, and let x be an element of A to B. Then f bar prime acting on x, the derivative, is equal to the limit as t goes to x of f bar of t minus f bar of x over t minus x, provided this limit exists. We should go back and look about distances in Rk, so that's what I want to do next. That's involved in limits, distances. So let's recall, given 2 points in Rk, say x x bar equal to, let me talk about this, x bar equal to x of 1, comma x of 2, all the way up to x of k, and y bar equal to y sub 1, comma y sub 2, all the way up to y sub k. Then, the distance in r sub k, and the usual methods, between x bar and y bar is equal to the sum as I runs from 1 to k of xi minus yi to b squared, and then all this raised to the 1/2 power. So that's the usual metric in RK, that's what we're looking at. Let me write that down. Is the usual metric in RK. Okay. Now, let's look at analogous fact to when we had functions just in R, but now looking at them in RK. I'm sorry. This is analogous fact for the complex value function. So here's what it says. It says, let f bar go from A to B into RK, where f bar of t is equal to f sub 1 of t, yada, 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 all the way up to f sub k of t. These component functions. Let x be an element of A to B, then f bar derivative at x exists if and only if and only if f prime, f sub 1 prime of x, f sub 2 prime of x, all the way up to f sub k prime of x exists. Okay, so each one of those has to exist. Moreover, the derivative of f bar at x will be equal to the derivative of f sub 1 at x, comma, the derivative of f sub 2 at x, comma, all the way up to the f sub k's derivative acting on x. So it'll be that k2. So this is a fact, as I said, it was analogous to a fact that we had about complex value functions. And I'm going to prove only one part of this. So we will prove this direction. That's all I'm going to do. And I don't think I got everything on the video here. So let me just say something a little bit about that f. Remember, the way we're looking at it from this other fact was that it's a tuple, k-tuple, of coordinate functions acting on t. Okay, so let's go ahead with this proof, at least this direction of the proof. Okay, so what we're going to let is let f bar go from A to B into RK. We're going to let x to be an element of the closed interval from A to B. And suppose F bar acting on T is equal to the tuple F sub 1 acting on T with F sub 2 acting on T, and so forth, all the way up to F sub K acting on T. And not only assume that, but and the F sub I prime acting on X exists for each I in 1 up to K. Okay. We will show that F bar prime of X exists. We will show that, and not only show that it exists, we'll show what it's equal to. That's how we show that it exists. That F bar prime of X is equal to the derivative of F sub 1 acting on X, F sub 2's derivative acting on X, all the way up to F sub K's derivative acting on X. That tuple is what F bar's derivative at X is going to be equal to. Okay? All right, so this is a matter of proving a limit exists, okay? So we're going to let epsilon be greater than 0, be given. Let me back up. Here's what we want to do. We want to show the limit as t goes to x of f bar of t minus f bar of x over t minus x is equal to this f sub 1 bar, prime acting on x, f sub 2 prime acting on x, all the way up to f sub k prime acting on x. So how do we show this limit is equal to this quantity? Well, here's what we do. Remember, t and x are in A to B, and so here's what we do. We'll say, we let, to show this limit exists, we let epsilon be greater than 0 be given. Okay? We need a delta greater than 0 such that for all t element of A to B with 0 less than t minus x less than delta, then the distance, and I'll say here in Rm, okay, or Rk, of the distance between f sub t bar minus f bar acting on x over t minus x, the distance between that and this f prime sub, or f sub 1 prime of x, f sub 2 prime of x, all the way up to f sub k prime of x, that this distance, okay, so this is a bar here, this distance is less than epsilon. That's what I want to show. Okay, so what is this distance? Okay, so we want, okay, well, what is this? We want the distance in RK between, well, what f bar of t is. Put it down right here. F bar t is the k tuple f sub 1 acting on t, f sub 2 acting on t, all the way up to f sub k acting on t. So that tuple, okay, minus, here, this would be the tuple f sub 1 acting on x, f sub 2 acting on x, all the way up to f sub k acting on x. Okay? Those two tuples subtracted from each other, all over t minus x, the difference between that and the point f sub 1 prime acting on x, all the way up to f sub k prime acting on x, that distance is less than epsilon. Okay, that's what I want to show. I don't know if that last part is very visible, so let me turn it just a little bit. Okay. There, maybe you can see it. So we're going to try to simplify a little further what it is that we're trying to show, and then hopefully be able to show that simplified version. So that means we want the distance in RK, okay, between, we can look at these, this first tuple, okay, we'd say it's f sub 1 of t minus f sub 1 of x over t minus x. This is using properties of RK, how we subtract two elements in RK, and how we multiply it by the scalar t minus x. And so here it'd be f sub 2 acting on t minus f sub 2 acting on x, all over t minus x. I'm going to run out of room. All the way up to f sub k acting on t minus f sub k acting on x, all over t minus x. That is the first tuple that we're talking about in RK. We want its distance between that and, sorry, I ran out of room. But here it's f sub 1 prime acting on x, f sub 2 prime acting on x, all the way up to f sub k prime acting on x. Remember, we know these exist as a number here. Okay, so we want to show that distance is less than epsilon. Well, finally, in terms of a translation, we want the square root. Remember, we had a sum, a raised to the 1/2 power, the square root of these differences here. So f sub 1 of t minus f sub 1 of x over t minus x minus f sub 1 prime acting on x. We want that guy squared plus, here I'm going to have f sub 2 acting on t minus f sub 2 acting on x all over t minus x minus f sub 2 prime acting on x. We want that guy squared. I'm really running out of room here. But plus the last term that's going to be here, plus, if you will, is an f sub k acting on t minus an f sub k acting on x, all that over t minus x, minus, I think I have that right, minus, it's going to be f sub k prime acting on x to be squared. We want that. We want that. I hope I can see it. I hope you can see it. We want that to be less than epsilon. That's what we want. Well, remember, each one of the coordinate functions derivative exists, so let's use that. So since f sub I prime of x exists for each I element of 1 to k, okay, then there exists, well, I guess we could write it that way. Then the limit as t goes to x of f sub I of t minus f sub I of x all over t minus x, okay, is equal to f prime of x. Okay? So that says there exists a delta sub I. We've been given epsilon, so there exists a delta sub I for each one of these f sub i's that is greater than 0. So I'm talking about this limit being in existence. Okay? So there exists this delta sub I greater than 0 such that for every t element of a to b with, come out of the limit here, so 0 less than t minus x is less than delta sub I. Okay? Then the distance f sub I of t minus f sub I of x over t minus x minus f prime sub I of x, that's going to be less than, well, it can be less than anything I want. I'm going to pick epsilon over the square root of k. That's what I'm going to pick. You'll see that that's important. It's something analogous to what we had done in analysis 1. So for all t element of a to b with 0 less than t minus x inside absolute values less than d sub I, or delta sub I, then this can be rewritten, absolute value, can be rewritten as f sub I of t minus f sub I of x over t minus x minus f sub I prime of x, that whole thing squared. That's what that's the value. It's going to be less than epsilon over the square root of k. So each one of these things. So, for all t element of a to b with 0 is less than t minus x is less than delta sub I, that says that it's f sub I minus f sub I of t minus f sub I of x all over t minus x minus f prime, f sub I prime acting on x. So this would be squared is less than epsilon squared over k. And there I'm just squaring both sides of the inequality that I had before. So now what we're going to do is we're going to let delta equal to the minimum of the delta sub 1, delta sub 2, all the way up to delta sub k. So we had these delta sub i's running from 1 to k. Now we'll get the minimum of that. And so now if we do that, then for every t element of a to b with 0 less than t minus x, inside absolute values less than delta, we have, okay, that distance that we wanted, oh goodness, is that square root, so this is in RK, of f sub 1 of t minus, it was f sub 1 of x, all over t minus x minus f prime, f sub 1 prime of x to b squared, plus, let me write down the next one, and then I'll go to the last one. So f sub 1, I'm sorry, f sub 2 of t minus f sub 2 of x over t minus x minus f sub 2 prime of x, that got to be squared, plus, all the way up to plus this last term. What's the last term? It's f sub k of t minus f sub k of x, all over t minus x, minus, it's f sub k prime, evaluated x, to be squared. Okay? I hope that's visible. All right? That's what we have. We have that guy. And then what we can do is we can substitute in for each one of these parts this epsilon squared over k, and when I make that substitution, what I'll be getting is something bigger. We're almost done with this part of the proof. Yeah, you can see it. Okay. Is less than, so it'll be the square root of epsilon squared over k plus epsilon squared over k plus epsilon squared over k. We're taking the square root of that. Well, first of all, this is the same thing as the square root of, we've got k epsilons here, and so this is k epsilon squared over k, which is just equal to, this is going to be the square root of epsilon squared, which is equal to epsilon. That's what we needed. Okay. So that says f bar prime of x is really equal to f sub 1 prime acting on x. It's this too. F sub 2 prime acting on x. All the way up to f sub k prime acting on x. Okay. And thus f bar prime exists. This is equal to this quantity as a limit. And so that is half the proof, the only half we're going to do. So I'll write down the conclusion that we've ended the part we wanted to do. Okay. Something we proved in analysis 1 is the following fact, is that if f sub 1 up to f sub k are real functions on a metric space, x and f bar is the mapping of big X into RK defined by F bar, I'll say a little x is equal to f sub 1 of x, f sub 2 of x, all the way up to f sub k of x. Then, f is continuous. F bar is continuous. And that's true if and only if each of F1 through Fk is continuous. That fact that we had proven in analysis 1 allows us to quickly get the following fact involving differentiation for vector value functions. So, thus, we have the following fact. Let F bar go from the closed interval from A to B into RK if F bar is differentiable at a point X element of A to B, then F bar is continuous at X. And this fact is very easy to get from the previous facts, the previous two facts. Okay? The one that we had to recall from analysis 1 is one we just did, or at least half the proof we did. Okay. All right, let's recall the following definition. Given 2 points, x bar equal to x sub 1, x sub 2 up to x sub n, and y bar equaling y sub 1, y sub 2 up to y sub n here, but let's call it k, so we're using the same notation. Doesn't matter, we would be consistent. These are n, r, k. Okay. Then x dot y, this inner product, if you will, is defined to be the sum as I runs from 1 to k of x sub I times y sub I. That's what we find. That is the inner product. Think of it as. Okay? And that's the first thing. And this is something we've used already in a previous proof, part of the proof that we did, is that x bar plus y bar, we've already used this now, is equal to x sub 1 plus y sub 1, comma, x sub 2 plus y sub 2, comma, all the way up to, x sub k plus y sub k. Okay. What we're going to do next is we're going to look at a theorem that is a differentiation theorem for vector value functions. Here's what it says. It says, suppose f bar goes from A to B into RK, and y bar goes from A to B into RK. This is not y, this is g. G bar. They are differentiable functions at a point x element of A to B. Then f bar plus g bar, and f bar dotted, this is inner product of g acting on x. These functions are differentiable and here is their differentiation rules. Part A, f bar plus g bar acting on x, it's all differentiable at x. And here, this guy is equal to f bar prime acting on x plus g bar prime acting on x. And for part B, this inner product between f bar and g, its derivative acting on x, is following the product rule, which is f bar acting on x times g bar, inner product here, g bar acting on x, the g bar derivative, plus f bar derivative acting on x, f bar derivative acting on x, inner product with g bar acting on x. Okay, let's we'll prove part B. And so note f bar acting on t is equal to f sub 1 acting on t, f sub 2 acting on t, all the way up to some function f sub k acting on t. It's that k tuple. And similarly, g bar is acting on some t is equal to g sub 1 acting on t, comma g sub 2 acting on t, all the way up to g sub k acting on t. Now, then, f bar, inner product with g bar, is derivative acting on x. But what that's going to be equal to is the limit as t goes to x of f bar times g bar acting on t minus all this thing acting on t minus f bar dotted with g bar, each one of them acting on t, I mean by that, all over t minus x. So what we're thinking of is you take f bar acting on t and then you inner product that with G bar acting on T. And here, this should have been X. So when you take that inner product, remember we've defined the inner product, I'll erase it on this side of the board, recall it. And so this is going to be the limit as T goes to X. This is a sum. And so F bar acting on T is that F sub 1 acting on T, F sub 2 acting on T, and the G bar acting on T is exactly this guy. When we do the inner product, it's going to be a sum as I runs from 1 to K. And here it would be F sub I acting on T times, so this is times, G sub I acting on T. So you do that multiplication, and you add them up, and that's what you get. Minus, here this is a sum, as I run from 1, this part is a sum, I run from 1 to K. Here it's F sub I acting on X times G sub I acting on X. And this is all over T minus X. And then we can rearrange these sums and take the limit of the following equivalent. Hi. That is, this is the same thing as the limit as T goes to X. Rewriting this would be F sub 1 of T times G sub 1 of T minus F sub 1 of X times G sub 1 of X. Okay, all over T minus X. Plus, the next one will be F sub 2 of T, G sub 2 of T, minus F sub 2 of X times G sub 2 of X, all over T minus X. And I don't have room, but we still have plus, so it's the limit of all of this. The last one will be F sub K of T times G sub K of T, minus F sub K of X times G sub K of X, all over T minus X. So it's the limit of all of that. Okay. Now, this, the limit of each one, is nothing more than, okay, let me write this. This is the limit as T goes to X plus F sub 1 times G, this time, acting on T, minus F sub 1 times G, acting on X, all over T minus X. Plus, we keep going in this way, breaking it up into several limits, K limits. Limits T goes to X, the final one would be, we would write this as F sub K times G sub K acting on T, minus F sub K times G sub K acting on X, all over T minus X. And each one of these quantities is nothing more than F sub, this is F sub 1, G sub 1, F sub 1, G sub 1. Yeah, I made a mistake there. This is going to be F sub 1 times G sub 1. This is the definition of this multiplication's derivative at X, plus, and I skipped some, let me add that here. It'd be F sub 2, G sub 2, that's derivative acting on X, all the way up to, here, this is F sub K times G sub K, its derivative acting on X. So that's where we are. And then we just apply the product rule, because each one of these, K times, each one of these multiplication, these dots are multiplication between real value functions. And so what you get is this is equal to F sub 1 of X times G prime sub 1 of acting on X plus F sub 1 prime acting on X times G prime G sub 1 acting on x. Okay, that's the derivative of f sub 1 times g sub 1. Plus, here it's going to be f sub 2 acting on x times g sub 2 prime acting on x plus f sub 2 prime acting on x plus times g sub 2 acting on x. Plus, we'll continue on. In the last term we're going to get is f sub k acting on x times g sub k prime acting on x plus f sub k prime acting on x times g sub k acting on x. Okay? And then this is equal to, if you want, you could just take the first terms of each one of these products and you get the sum as I runs from 1 to k, and it would be f of sub I times g sub I prime, okay, each one of them acting on x. So let's do it this way. F sub I acting on x times g sub I prime acting on x plus, and so that's this term, and all the way to this term. Plus the next sum is I running from 1 to k, and it would be here f sub I prime acting on x times g sub I acting on x. Those are the second terms in each one of the product rule expansion that we've gotten. And here, what this is nothing more than this guy's f bar acting on x dotted, okay, or f bar dotted. So this is the inner product with g bar prime, because that's what this guy would be, and acting on x plus, here this is going to be f bar's derivative, inner product with g bar acting on x. That's what it is. Okay, and that ends the proof. All right, ladies and gentlemen, that's enough for this video lecture 7. Thank you very much for your time and patience.